There you are. How are we doing, Ignite students? It's a great day because today we're going to talk about electromagnetic spectrum, radiation, and all sorts of crazy things. You, right now, are being irradiated. Sounds pretty scary. There is radiation falling on you right now. It's traveling around you, through you, landing on you. It's everywhere. Some of you may be thinking, well, I'm in a pretty dark room, so there's not a lot of light. There's light from the screen coming at you, right? There is light from the window or whatever. Maybe you're in a pitch black room, but there's at least light from the screen. Even if there's not light from the screen, there's radiation passing through you right now. Radio waves. Yep, they're there. Maybe some small gamma rays, X-rays, infrared, microwaves. Stuff's all around us. Not a lot of it, but we've got to figure out what it is, where it comes from, where it's going. Okay. Light is a wave. Light is a particle. Both of those are period, full stop, accurate sentences. That's really confusing because it can't be two things. It either acts like a little bitty ball, you roll it around and you hit things and it runs into other things, or it acts like a wave and it moves and it has power. Light has properties of both. This idea, this debate went on for decades. People raged. My experiment says, look, light is like a ball. It hits another one, it bounces off, and waves don't do that. Waves go through each other. Then someone else would do an experiment and say, look, here, I did this experiment, and now here are the results. It shows that it's a wave because it went through this thing, and it didn't end up where if you threw balls, it didn't end up where they would have. It went through like a wave. Back and forth and back and forth. Light has properties of both. And depending on how you manipulate the experiment, you can get either result. It's very weird. In fact, it's a little bit of both. It's like tiny packets of waves. Maybe that's a way to think of it. Photon is a little bitty wave packet. And the packet gives it the small ball-like properties, and it is a wave. It's very, very detailed and very complicated. All right. So let's talk about a wave first. We're going to treat it like a wave because we're worried right now about wavelength. We're worried about frequency because that's going to determine everything. So let's look at waves. Here we go. First one, nice and easy. This is a transverse wave. Okay, it actually says transverse wave first there. This is what we normally think of when we think of a wave. You've got a crest and a trough. You have an amplitude. Amplitude is height. It's that simple. Amplitude is height, but it's measured from the middle. It's measured from the middle. It is not top to bottom height. If there were no wave, all this would just be a flat line. So amplitude is how far it got disturbed up or down. Amplitude is the displacement. It is not the total top to bottom. Or you could think of it as half. I don't know. Wavelength is the distance between two crests. That's the Greek letter lambda. It's the symbol for wavelength. Okay. Wavelength you can measure between peak and peak. You can measure it between trough and trough. It's the same distance. If you try and measure from the middle, you better be careful because middle to middle is half of that. Middle on the way up to middle on the way down. No. Middle on the way up, middle on the way up. From here to here is the same wavelength. So usually crest to crest is going to be the easiest way to pick it out. Find that. This is a transverse wave. Those are nice vocabulary words. Thought. Okay, so here's a question for you. What's the difference between red and blue? Not that I happen to be wearing both today, but what's the difference between red and blue? How does your eye tell the difference? How do you know the difference? What's the difference between green and orange? What's the difference? It's the wavelength of the light. It's the wavelength, the length of the wave that hits your eye. So visible light, Roy G. Biv, rainbow, right, Roy G. Biv, comes into your eye, and depending on the length of the wave of that light, you see a different color. You see a different color. That thing behind me, that's what a light wave looks like. So what we've got purple going up and down, and then we've got green going flat, right? So you've got purple up this way and green flat that way. Light is an electromagnetic wave. It's an electromagnetic wave because there's an electric part and there's a magnetic part. It's really complicated, but we can treat it just like one wave because the electric and magnetic parts are related. So we don't need to know that there's a part going this way and a part going this way, and we don't care about all that. All right? Electromagnetic wave is one type of light, but the electromagnetic spectrum, that's all of the types of lights. There is nothing else. There's not something on the end of this chart out here that we just haven't discovered yet. Nor, let's try that again, nor is there some, there we go, nor is there something over here on this end that we haven't discovered yet. Okay, well, I'll tell you why. The math bears that out. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma ray. The difference between an X-ray and a microwave is exactly the same as the difference between red and blue. It's wavelength. It's all the same stuff. It's just a wave. So the difference between a radio wave and a gamma ray is not Incredible Hulk. The difference is color. So if visible right here, this little tiny slip right here, it doesn't even really, this one right here, that's all visible. From this Roy, red, orange, yellow, green, blue, Roy G. Biv, right? The difference from here to here, this is actually shrunk down. This is a really, should be narrower. They just wanted to expand it. Should be really small and is right in here. The difference between green and yellow is the exact same. You change the wavelength, and that's how you change from radios to microwaves. That's it. On this end of the spectrum, over here, all right, on your left end, radio, long wavelength, huge long wavelength, literally the size of buildings, all right? And then radio waves we would tune our FM or AM stations to, all right, are literally meters the size of people. Microwaves, smaller, are used in microwaves. They're also used in cell phone receivers and cell phone towers. All right, so the wave is now shrinking. Infrared is heat. If you could see an infrared, it would look like Predator or a FLIR camera. The FLIR is a brand. It would be the heat vision cameras. They see radio waves. They see waves in the infrared. Then we've got all the visible light. And then this is just down here for the size of things. UV light, what's ultraviolet light? Well, that gives you a sunburn. And then that gives you skin cancer if you get too much of it, right? That is slightly damaging. This is what we see. This is what we feel. You feel infrared is heat. X-ray are small enough to go through soft tissue but bounce off of hard tissue. That's why they're good for X-rays. Gamma rays, even smaller. We've shrunk the wavelength all the way down to this. As the wavelength shrinks, the frequency is the number of waves per second. If you stood still and counted how many waves went flying by you per second, that's frequency. Well, if the wave is really long, one wave passes per second. But if the waves are really short, you've got thousands, millions, hundreds of millions. So here you've got 10,000, right? And up and up and up. And your frequency goes up as the wavelength gets shorter. So wavelength gets shorter, frequency goes up. Temperature of the stars, we'll talk about that. There is so much here. All right, we're going to talk about this whole spectrum for a while. All right, there is a lot to this. These two, wavelength and frequency, are related. They're related in a simple formula. that the speed of light, like visible light, is wavelength times frequency. So as this one gets bigger, this one gets smaller. Well, that makes sense, because if they're going to multiply, if they have to equal the speed of light, then that makes sense, right? So if I want to multiply two numbers and get to 120, okay, if I say 120 is a big number times 1, that's a small number. Well, then if I want to make this one 2, I have to make this one 60, right? If I want to make this one 3, this one's got to go down to 40. So as this one goes up, this one comes down. And when you multiply those two things, you get the speed of light. All right. Where are we at today? Oh, by the way, speed of light is not just the speed of light. It's the speed of radio waves. It's the speed of gamma rays, X-rays, ultraviolet. All of this is the same stuff. So all of this travels at the same speed. All right. That's for later. This same picture, some more uses. This is kind of interesting. There we go. AM radio, FM radio. It shows you they're spaced out. Cell phones are in here. Microwave ovens. Okay. The heat coming off of us, the light that predator would, or infrared camera would see, or a FLIR camera would see, night vision, that's right there. Your remote, that operates in the infrared. Visible light's this narrow spot right in here. All right. Sunburn, that's ultraviolet, X-rays, gamma rays. All right. What are gamma rays good for? Nuclear power. There we go. Okay. Science in a minute. I'll have all these links up. This one is good to explain infrared and how it's used and how it can be used. This one is super simple, like really beginner stuff. This is 10 minutes that we're probably going to stretch over several days. So if you want the super short version, you can watch this, but every single thing he says is like a big topic, and we're going to talk about that. Maybe we don't even get to all of it, but there's a lot in this video. It's good. But all right, electromagnetic spectrum. There is a lot of stuff. We're going to talk more about this. Have a great day. Your tests are graded. They should be updated. Guys, keep up with your work.